Good morning, everyone. I will give a quick introduction to this topic of measuring building component airtightness before the three main presentations. As we all know, air infiltration has many consequences on the building and its occupants. We can mention drove effect, acoustical insulation, transport of odors, pollutant penetrations, even problems fire safety, and this is obviously not exhaustive list. And the major point with air infiltration is that it impacts energy, health, and comfort of the occupant. Last decade's research in airtightness really focused on energy, and this results in a tremendous increase of a number of fan pressurization tests or blower door tests conducted in practice. This has really good impact since it helps to improve airtightness, to develop databases, national databases all around the world, and to develop guides for architects and contractors on how to build airtight buildings. However, the fact that we promote fan pressurization test has also a couple of drawbacks, because the fan pressurization test reports airtightness at 50 Pascal, while air infiltration in usually it's more about 0 to 20 Pascal for pressure difference, and it assumes that leakage are uniformly distributed along the envelope. And the problem here is that the consequences and the amount of air infiltration depends on leakage location and distribution. For the consequences, it can be quite straightforward. For example, with the internal versus external leakage, we really suppose that internal leakage will have less effect, for example, on the energy consumption than external leakage will have. For the amount of air infiltration, it's a bit more tricky, but I really invite you to read the work presented at the 40th AIVC conference by Steve Rogers, because in this work he showed that for three different distributions of leakage along the envelope, three different distributions that would result in the same fan pressurization result for the fan pressurization test, he found really high variation of air infiltration at 1 Pascal of pressure difference. And so with that said, we are looking now on how evaluating the quantifying building component airtightness in parallel with all building performance. Regarding the method for quantifying building component airtightness, we have three categories. There are the numerical models, which consist in the estimation of airflow through the development of fundamental equations of fluid mechanics. We have the laboratory testing, which is the measurement of the relation between pressure difference and airflow for the given component, but in a highly controlled environment, while in situ testing is measuring the same relation, but this time directly on site. Each method has obviously its advantages and its drawbacks. For the numerical models, we have no planning constraints, since we can do these modeling in parallel with the construction or the retrofitting context. It's quite easy to interpolate those models. If you have one model that is validated, we can it's much more easier to change the size of the material than it would be for a test. And we have the models that can be transferred to larger models. For example, if you have quite a good validated crack model, you can easily transfer it to, for example, a multi-zone model to model the indoor environment of your building. On the other hand, you have your drawbacks, that the numerical models are still a representation of reality. You are not measuring something that exists, and there are a lot of validation work that are needed for these type of model. And nowadays we have quite a lack of crack data to make these models really significant and really relevant in current practice. Regarding the laboratory testing, we also have no planning constraint. That is quite an important advantage. We can control variables, for example, temperature or relative humidity, that are that are used during the test, and we have quite a good visualization of the components that can be very useful when you do, for example, a laboratory test with smoke detectors, and you can really point out easily where the leaks and where the defects of the measured components are. The drawbacks are obviously that it's not the real configuration. Usually we test one component alone, although it's not always the case. We can sometimes test whole facades, but usually we test only the component alone, and the setup are really in perfect situation. You don't have dust that can impact the performance of your tapes, for example. You always have enough spaces to build your component, while it's really not always the case in directly on site. For the in-situ testing, the main drawback is obviously the fact that it's in real configuration, so it includes an uncertainty that can come from workmanship or supervision quality, and we know that these factors are very, very important in the context of airtightness, performance of building components. The drawbacks, on the other hand, are that you have the planning constraints, so you have to work in parallel with other workers on site, and this can be sometimes quite difficult to manage. And the environment is completely uncontrolled. You can have really high winds, for example, that will impact highly your test and the performance of the components you are testing. This webinar does not focus on a new topic. It's quite old, in fact. In the 34th technical note of the AIVC, the subject was already here, and this technical note was written in 1991. However, we have quite new perspectives today because we see a regain of interest in health and comfort of the occupant, and we have the new directives for retrofit in Europe, and we see that these type of measurements are usually preferred in retrofitting context. So today we will have three presentations on three different techniques. Victor will talk about the reductive sealing technique. I will then talk about the direct component test, and Benedict will finish with an acoustical method. So I hope you will enjoy this webinar, and thank you.